Hey there. Have you ever just looked around and wondered what's holding everything together? I mean, from the salt in your shaker to the device you're watching this on. Well, the answer is all about the invisible social lives of atoms. Today, we're kind of crashing their exclusive party to figure out the chemical bonds that build our entire world.
You know, it sounds like a pretty simple question, right? But the answer is, well, it's huge. Think about it. The reason your chair is solid, the reason water stays, wet, it all comes down to these powerful, totally invisible forces that lock atoms together. We call them chemical bonds, and they are, quite literally, the glue of the universe.
Okay, so why? Why do atoms even bother connecting in the first place? Well, it all boils down to one single motivation: this deep, fundamental quest for stability. See, in the world of atoms, you've got this super exclusive group, the noble gases. They are the cool kids on the block. They're perfectly stable, they don't react with anyone, they've basically got it all figured out. And every other atom? They just want to be like them.
So how do other atoms get in on that action? How do they get that noble gas status? It's all about one thing: getting a full outer shell of electrons. Seriously, that's it. That is the one and only goal that drives everything. Whether an atom is going to give away, take, or share its electrons, the end game is always the same: get that stable, complete outer layer.
All right, so let's get into the first strategy atoms use. You can think of this one like a really clean, simple transaction. You've got one atom that has something it needs to give away, and another atom that desperately needs to take it. Welcome to the world of ionic bonding.
So let's meet our players. On one side, you've got sodium. It's a metal, and it has this one lonely electron in its outer shell that it is just dying to get rid of. And on the other side, we've got chlorine, a nonmetal that is so close, just one electron away from having a full shell. You can probably see where this is going, right? It's a match made in chemistry heaven.
And this, right here, is what we call an ionic bond. It's what happens when there's a complete transfer of an electron from one atom to another. This creates ions, atoms with a charge, and then this powerful force, called electrostatic attraction, holds them together. Think about when you rub a balloon on your hair and it sticks. That static cling. This is like that, but on an atomic scale, and it's millions of times stronger.
And boom, here's the moment it happens. Sodium hands over its electron, and in doing so, it becomes a positive ion. We call it Na+. Chlorine snaps it up, becoming a negative ion, Cl-. They're not neutral anymore. And what do we know about opposites? They attract. That powerful attraction is the ionic bond.
And I really want to stress, this is not some weak connection. The phrase strong electrostatic forces sounds technical, I know, but just think of it as atomic superglue. It takes a ton of energy to break these things apart once they've formed.
So, because this bond is so incredibly strong, it gives these ionic compounds, like your everyday table salt, some really unique properties. For one, they have ridiculously high melting and boiling points. That's why they're solid crystals, at room temperature. And then there's this really interesting thing they do with electricity.
Okay, so what's the deal with that? Why do they only conduct electricity when they're liquid? Well, look here. When it's a solid, those ions are locked up tight in this rigid crystal grid. They can't go anywhere. But the moment you melt it or dissolve it in water, boom, the ions are free to move around. And if they can move, they can carry an electric current. It's really that simple. No free-moving charges, no electricity. Okay, but what if you have two atoms and they both need electrons? Nobody wants to be the giver. You can't have a transaction if no one's willing to sell. Well, in that case, they have to cooperate. This brings us to our second strategy, covalent bonding, where, sharing is caring. So this typically happens between two nonmetals. Neither one is strong enough to just rip an electron off the other. So instead, they compromise. They each put an electron into the middle, creating a shared pair. Now, that negative pair of electrons is attracted to the positive centers, the nuclei of both atoms at the same time, and that's what holds them together. It's a bond built on teamwork.
But here's where it gets interesting. Covalent sharing can go two very different ways. On the one hand, you can form these small, separate little packages called simple molecules. Think water, H2O, or the oxygen you're breathing. But on the other hand, you can have every atom linked to every other atom in a massive, never-ending network. We call those giant structures.
Let's stick with the simple ones for a sec. This is super important to get. The bonds inside one of these molecules, say a single water molecule, are super strong. But the forces that attract one water molecule to another water molecule, they're actually really weak. And since those are the weak forces you have to overcome to, say, boil something, it's pretty easy to do. That's why so many of these are liquids or gases at room temperature.
Okay, but now imagine a different scenario. What if every single bond was one of those super strong covalent ones? What if there were no weak forces between molecules, just one giant continuous molecule? Well, that's when you get a giant covalent structure. And let me tell you, the properties change completely.
And there is no better example of this than carbon. In a diamond, every single carbon atom is bonded to 4 other carbon atoms. This creates this incredibly rigid, strong 3D lattice. The result? Diamond is the hardest natural substance we know. But now look at graphite. What's in your pencil? It's also pure carbon, but here, each carbon only bonds to 3 others, forming these flat sheets. The bonds between the sheets are really weak, so they just slide past each other. That's why graphite is soft and slippery. And that extra electron that's not in a bond, it's free to zip between the layers, which is why graphite, a nonmetal, can actually conduct electricity. It's just wild. Same atom, totally different worlds.
So we've had the givers and takers, we've had the shares, but there's one more strategy. This last one is totally different. It's a group effort, a full-on communal system, and it's unique to metals. See, in a piece of metal, the atoms are pretty chill about their outer electrons. They don't really hold on to them tightly. Instead, all the atoms basically throw their outer electrons into one big community pod. So what you end up with is this grid of positive metal ions just sitting in a sea of all these free-floating delocalized electrons. And the bond? It's the attraction between all those positive ions and that negative sea of electrons swarming around them.
And this sea of electrons idea? It explains everything we know about metals perfectly. That attraction between the ions and the sea is really strong, so it takes a lot of heat to break them apart. That's why metals have high melting points. And since you've got a whole sea of electrons that are free to move, of course they conduct electricity and heat like a champ. And this is the cool part. Because the ions are floating in this flexible sea, you can push them around. The layers can slide over each other without the whole thing shattering. That's what makes metals malleable. You can bend them and shape them.
Okay. Wow. We've met the whole crew now. The ionic givers and takers, the covalent sharers, and the metallic commune. So let's bring them all together for the final showdown, the ultimate comparison.
This is it. This is the big picture. If you want to understand everything, just look at that top row. What are the electrons doing? Are they transferred from one atom to another? That's ionic. Are they shared between 2 atoms? That's covalent. Or are they delocalized in a giant sea? That's metallic. Seriously, that one thing, how the electrons behave, dictates everything else. The types of atoms involved, the forces at play, and especially key properties like conductivity.
So you see, it all comes back to these relationships. The give and take of ionic bonds making salt, the teamwork of covalent bonds making water, the community effort of metallic bonds making a steel beam. These fundamental atomic interactions are literally the architects of our entire physical world.
And that kind of leaves us with a pretty big thought, doesn't it? For a long time, we've been able to understand these bonds. But now we're starting to design with them. We're creating new materials from the atom up. So if these tiny fundamental relationships built the entire world we see around us, what happens when we start building with them on purpose? What will they build for us next?